This problem, we've got water flowing through a splitter and then a mixer. So water flows through a pipe, splits into two parallel pipes, and then the fluids mix into another. We're told that all the pipe is commercial steel. The equivalent length of branch 1, which is the top pipe, is in this drawing is 75 meters. The equivalent length of branch 2 is 50 meters. The elevation at the split point is the same as the mixing point, so we don't need to worry about elevation changes. We're told that branch 1 is 2-inch Schedule 40 pipe and branch 2 is 1.5-inch Schedule 40 pipe. The pressure drop across branch 1 is fixed at 100 kilopascals. We want to determine the volumetric flow rate in each branch and the total volumetric flow rate. And then as a second part that we'll deal with at the end, what information could be obtained if the pressure drop were not provided. So what this problem is going to illustrate is how to apply the Bernoulli equation to a system where you have, for example, a network of pipes. And because we do not have a perfect split in that we have different diameters for branch 1 and 2, we also have different lengths for branch 1 and 2. It's not a simple calculation. There are competing factors that are going to influence the flow rate. Now we are told that we know the pressure drop in branch 1, and that is controlled at 100 kilopascals. And so based on this information, how do we calculate the flow rates in these two branches? And so since we're only asked to find the flow rates, we don't need to, in the branch, we don't need to worry about the overall system. We can ignore the split point, we can ignore the mixing point, and all we need to worry about is the flow through this branch, the upper branch as it's drawn here, and the flow through the lower branch, or branch number 2. So we can apply the Bernoulli equation over both branches. Another thing is for each branch, this is steady state flow, this is incompressible fluid. Each branch has a constant velocity, a constant cross-sectional area. We can kind of think ahead into our Bernoulli equation that the velocity terms are going to cancel out. Also, we're told that the elevation differences, although we're drawing these as a top and a bottom, you can think of these as being a top view where there is no elevation change whatsoever. So what I've got here, just for reference, I've got our Bernoulli equation in general form, and then what I want to do is bring the Bernoulli equation, apply the Bernoulli equation to each branch. And so for branch 1, if we apply the Bernoulli equation to branch 1, we have the pressure at we'll call this inlet to 1, and we'll call that P1A. All right. The velocity, we don't need we don't need to worry about the velocities, because remember, the velocities are constant across the branch. Those are going to cancel. The elevations are going to cancel from the inlet to the outlet of each branch. We don't have any head added, right? What about, and we don't have any head extracted, but we do have head loss, right? And the head loss is included in this equivalent length. And then, of course, we know the pressure at the outlet of the branch. So we can write this, and so for branch 1, I've written this as P1A over rho G minus the head loss in branch 1 is equal to P1B, that is the outlet, over rho G. And so we can simplify this to P1A minus P1B over rho G is equal to the head loss for branch 1. We can do the same thing for branch 2. So branch 2, P2A at the inlet, head loss across this is equal to the P2B, the pressure at the outlet of our branch. And so we get these two equations. Now, we are asked to find the flow rate. Where is the flow rate in these equations? Well, the flow rate is buried in the head loss, right? The flow rate, because the head loss is going to be a function of the Reynolds number, which is a function of the flow rate. So for the head loss, we did not have any fittings. We are not doing any elbows or bends in this, but what we were told is the equivalent length. So that actually includes whatever kinds of fittings, as well as the actual length of these pipes. And so since we're dealing with water, we're going to assume turbulent flow, and this is something that we'll check at the end. But when we have turbulent flow, then what we need to do is we need to include that into our fanning friction factor. And so I've written the fanning friction factor for branch 1 with U1 and ID1, and then I've also written it for branch 2, where again I've expanded the Reynolds number to include explicitly the velocity. The head loss for each of these is going to be related to the fanning friction factor, which is going to have this equation. So the fanning friction factor goes in here, which has velocity, and then of course we have the velocity squared for each of these two. So if we substitute in for F1 into each of these equations, we get these equations for the head loss. So this is just an algebraic substitution of the fanning friction factor into F1, fanning friction factor F2 into F2 here. You get this big complicated equation. And then we can take the head loss and we can substitute it into each of these equations for the Bernoulli equation for each of these branches. And so that is given here. And so I'm doing these in parallel for branch 1 and branch 2. I've taken these Bernoulli equations now and moved everything over to the left side so that then I can use the MathCAD root function to solve for the respective linear velocities U1 and U2. And so set this up in MathCAD. I initially need to provide a guess for U1 and U2. I'm going to just guess 1 meter per second, which is a nice round number. Set up the root function, and then I ask MathCAD to solve for it, and I get these answers. So and remember, branch 2 is the 2-inch nominal, branch 1 is the 2-inch nominal, branch 2 is the 1.5 nominal. You see we get different linear velocities, all right? So 2.5, 2.6, about 2.8 meters per second in branch 2. Does that make sense? Well, we've got a larger inner diameter for branch 1, and so we would think that the velocity would probably be a little bit smaller. But then you look at the fact that branch 1 is a length of 75 meters and branch 2 is 50 meters. So there's going to be a different, not only because of the diameter, the inner diameter differences, but because of the equivalent length, there's going to be different resistances to flow. And so we actually have to go through and calculate. This is not just something that generally one can look at and kind of figure out exactly what's going on with these problems. So anyway, we have to trust the math. So these are our values for the linear velocity. From this, we can then calculate the mass flow rate and the volumetric flow rate. We calculate the mass flow rate. We get about 5.6 kilograms per second remember, branch 1 is a larger branch. The mass flow rate is 3.6 kilograms per second. So that makes some sense. That this is a larger diameter. We have about the same velocity, and so we should have a larger mass flow rate. Volumetric flow rate, again, is proportional because of the densities here. And then the last thing we need to do is we need to check that assumption of turbulent flow. So remember, the Reynolds number needs to be greater than 2300. We get 1 times 10 to the 5th for both of those, so that is definitely turbulent flow. And so our original assumption of turbulent flow was fine. So what I want to do is it's difficult to kind of summarize these in MathCAD, but I just wanted to give a little comparison here. Remember branch 1, the 2-inch nominal. Branch 2 is 1.6 nominal. The lengths were different. So branch 1 has less resistance based on inner diameter, less resistance to flow based on inner diameter. But you can see it has more resistance to flow based on the equivalent length. And so the reason why we can't just look at this and kind of eyeball it and do the calculation in our head is it's a little more difficult to figure out how these two factors interplay to affect the actual flow rate through the system. And so you see that the head losses are actually quite similar for both of these cases when you take into account the lengths and the velocities. The head losses are very close, and you see that our mass flow rate difference is about 1.5 times greater in our larger diameter pipe, but the linear velocities are about the same. So anyway, that's a calculation of applying the Bernoulli equation to a network of pipes.